Hi everyone, let's continue. Okay, we're going to discuss the properties of power series. Suppose the power series ck(x to the k) and the power series dk(x to the k) converges absolutely to function f and function g respectively on an interval I. Okay, the first property, sum and difference. The power series of ck plus or minus dk x to the k converges absolutely to f of x plus or minus g of x on I. Okay, so we can add or subtract two power series, and then they will converge to the sum or difference of those functions. Okay. Second property, multiplication by a power. The power series, when we multiply a factor x to the m, you can see we can move this inside and we can combine the exponents. It becomes x to the k plus n. So this guy converges absolutely to x to the m times f of x on I, provided m is an integer such that k plus m is greater or equal to 0 for all terms of the series, because we still want to make sure the power series is still a power series, so all the powers are positive powers, positive exponent. Okay? So that makes sense, right? When we multiply it by an extra factor of power x to the m, then it converts to f times that extra factor of x to the power of m. Okay, 3, composition. If h equals to bx to the m, where m is a positive integer and b is a real number, the power series ck h of x to the k converges absolutely to the composite function f of h of x for all x, such that h of x is in the interval I. Okay, so this, you can see when we plug in b x to the m here, we get b to the k x to the m k. Okay, so sum of ck. So this guy is still a power series, so it converges to f of b x to the m on I. So far so good. Okay, so that is combining power series. Next, let's differentiate and integrate the power series. I also want to emphasize when we add or subtract two power series, multiply a power series by a number, the interval of convergence is still I, and for the composite function, you're going to make sure h of x is also in I. Okay, so the interval of convergence is kind of the same as before. But when we differentiate and integrate power series. Okay, so let f be defined by the power series on the interval of convergence I. First, f is continuous function on I. Okay. Second, the power series may be differentiated or integrated term by term, and the resulting power series converge to the derivative of f or the antiderivative of f, respectively, at all points in the interior of I. So we guarantee that for the interior of the interval I, the series converges. But at the endpoints of I, we don't know, so sometimes we need to check the endpoints. Okay, so here, yes, C is the arbitrary constant, and so one of the antiderivative. Okay, so when we differentiate and integrate the power series, we guarantee convergence in the interior points of the original interval of convergence. But at the endpoints, we don't know, so we need to check the endpoints. Okay, so keep those in mind. Let's look at example 2. Given the geometric power series, so sum of x to the k is 1 plus x squared. It converges to 1 over 1 minus x if absolute value of x is less than 1. Okay, so find the power series and the interval of convergence for the following functions. Okay, so remember two important concepts in this chapter. We have power series and we have functions. Okay. So given a power series, how do you find the function that it represents? Or given a function, how do you find the power series? Okay, for this direction, okay, so for this direction, one method is we can use the common power series formula and use the property of power series, which is what we're gonna do right here. Okay, there is another method is use the Taylor series formula. Okay, this is gonna be in session 9.3, so we'll discuss in the next session. Okay, so first, the common power series. Okay, so we know that 1 over 1 minus x equals to, so we have this power series converge to that. Okay, so how about our new function? Okay, let's compare. What's the difference between this guy and this guy? Well, it looks like we have an extra factor of x to the 5th. Do you agree? Yes. And then now we know this guy equals to sum of k from 0 to infinity x to the k. So let's plot it in. And then now I can move x to the 5th inside. We get x to the 5th, x to the k. Alright, and we can also combine them together. It becomes x to the k plus 5. Okay, so for the power series, I hope that you can always express it in terms of like a sum of ck x minus a to the power of k. So express your power series into the standard form, and the function is f of x. Okay, so you can see the here we have the center is 0 and then ck is all 1. Okay, so what we have been doing, we multiply the power series by powers of x. Will that change the interval of convergence? No. Okay, so we call the interval of convergence is -1 to 1. Okay, that's our I. So now our new interval of convergence is still the same, right? Because remember when we multiply by a power series by powers of x, it won't change the interval of convergence. It still be the same I, okay? So far, so good, everybody? So you can use the properties of power series to figure out the interval of convergence. Okay, you can also use the ratio test to figure out the interval of convergence. Okay, so, and then let's continue. What's the difference between part B and 1 over 1 minus x? So we want to express is like 1 over 1 minus something. What's that something? I would say -2x squared. So far, so good, everybody? Yeah, so we want to express in this in that form. So it's like, we replace x by -2x squared. Okay, so now we know this guy is k from 0 to infinity, and it was x to the k. Now we replace x by -2x squared. So far, so good, everybody? So you compare this guy here. Okay, we compare, we realize, it's like we replace the old formula, the x, by -2x squared. Then the series x to the k becomes -2x squared to the k. Okay, so what is that? So let's split. So it's -2 to the k. X to 2 to the k is the same as x to the 2k. Okay, so please express your power series into the standard form, okay? So that's the standard form. Okay, next, how do we figure out the interval of convergence? Well, we know that the old series, okay, so let me put here the old, okay, let me figure that out. Okay, and point it out. So the old series converges for absolute value of x less than 1. Okay, then our new series, because we're doing composition. Okay, so our new series, converges for, we replace x by -2x squared. Okay, wow, what is that? Oh, negative cancel out, so we have 2 and then square less than 1. Okay, so that's the same as saying 2x squared between 1 and -1. Oh, this guy is always true because 2x squared is always positive. So that's why we just look at this guy. Okay, so we have x squared less than 1/2. So what does that mean? That means when you take the square roots, absolute value of x is less than 1/√2. Okay, and that means x is between -1/√2 and 1/√2. So everybody, you gotta be careful. You cannot like how you solve equation. You cannot say, oh, x squared less than 1/2, so x less than plus or minus 1/√2. What does that mean? 1/√2 is here. Negative 1/√2 is here. Less than both of them. What do you mean by that? No, not this case. So this is wrong. You cannot do it like this. You can think about when you take the square root of x squared is like absolute value less than square root of 2. That means x is lying between 1/√2 and -1/√2. Okay, so that is our interval of convergence. It's -1/√2 and 1/√2. So far, so good, everybody? Okay, let's continue. So part C. Oh, part C, this is harder than what we have learned before. Okay, so what's the relationship between that and the 1/1 minus x? Okay, so I may need more space, so okay, then I can have more space in part C. Okay, so first of all, you realize, oh, 3x to 7, let's move it out. Then I have the 1 on top, right? Okay, 1 on top is not only 1 on top. We want to express as 1/1 minus x. So we want to have this is 1. We also want to have this guy is 1. So how do we achieve that goal? So we can try to factor out the 5 there. So we factor out the 5 there. What's left? Well, then this 1 minus, when you factor out the 5, is like you multiply by 5, you divide it by 5, and you move the 5 out. So this is what we get. Okay, so now you can see here, this is 1, this is 1. Awesome. And so this is the same as you have this extra power moving is outside. Okay, this guy is gonna be, we can use the power series. We replace x by what? So you're gonna use that formula and replace x by 4x over 5. So then this is k from 0 to infinity, and x to the k become 4x over 5 to the k. And what is that? Okay, we gotta move the 3x7 over 5 inside. And this is like 4 to the k, x to the k over 5 to the k. Okay, so combine all the coefficients together. Right? This is how we make it into the standard form. Put the coefficient together. Combine the x together. So 5 times 5 to the k is 5 to the k plus 1. And then here we have x to the k. X to the k times x to the k, 7 is x to the k plus 7. So far so good, everybody. So this is our new power series. Okay, so how will the interval of convergence change? Well, when you multiply by a factor, it won't change. But when we're doing composition, it will change. So our series converges when the absolute value of we place x by 4x over 5. Less than 1, right? So 4x over 5 between 1 and minus 1 multiplied by 5 divided by 4, we get x. Okay, so that's why our new interval of convergence is negative 5 over 4 and 5 over 4. Okay, so far so good. And we don't need to check the endpoint because the properties of series, when you add or subtract the power series, when you multiply by powers of x, or when you do composition, the endpoints still stay diverged. So in the previous series, at the endpoints it diverges, but now at the endpoints it also diverges. So it's consistent. But when we differentiate or integrate the power series, we gotta check the endpoints. Okay, so because we only guarantee convergence in the interior points, but at the endpoints we don't know, we need to check. Okay, part D. Differentiate the power series term by term. Okay, to find the power series for f prime. Okay, let me recall. So we have the power series x to the k, well that's 1, x squared, x cubed plus that's 1 over 1 minus x for x, that's the 1. Okay, so we can differentiate the power series term by term. Okay, so let's differentiate the middle guy first. Derivative of 1 is 0. Derivative of x is 1. Derivative of x squared 2x. Derivative of 3x squared Derivative of x cubed is 3x squared. I already say the answer. Okay, so how do we differentiate this series? Okay, it's still k to infinity, but here when we differentiate the k, x to the k, it becomes k x to the power of k minus 1. Okay, so this is what we get. So the only thing that we're not certain is what does k start with. So how do we figure out this number? Well, look at the first term. The first term, what k you plug in your expression, you can get 1. Well, it looks like k equals to 1, right? When k you plug in 1, 1 minus 1 is 0, x to the 0 is 1. So that's why here k equals to 1. Okay, so you can figure out the formula by differentiating this guy, but for the k, what k you start with, you actually need to look at the first term of the power series to identify, oh, my index should start with 1. Okay, all right. What's next? Sometimes students might see, instead of this, you might see some students or some answer like 0, and then this is k plus 1 x to the k. They are the same. It's just this index start with 1, that index start with 0. They represent the same power series. Okay? All right. Next, we can differentiate the function. Well, what's the function? Well, the derivative of this function, how do we differentiate? Well, we use the standard form. This is like 1 minus x to the negative 1. Take the derivative of that is minus 1. This is like chain rule, right? U to the negative 2 times u prime. But your u prime is negative 1. So this is negative 1. It cancels with that negative 1. So we have 1 over 1 minus x squared. So far, so good? Okay. So that's how we find the function and we find the power series. We know, we guarantee, so we know. Okay, series converges for x less than 1, okay? But still need to check the endpoints. Okay, because we only guarantee convergence for the interior points. The interior points is exactly minus 1 and 1. So let's check the endpoints. So at x equals to 1 and at x equals to minus 1. When x equals to 1, what happens? So let's plug this in here. Okay, so when we plug in x is 1, we have k from 1 to infinity. X is 1, so it's just k. Wow, k, you're adding a lot of positive number. Of course, it will diverge. When k equals minus 1, we get, when x equals to minus 1, then we have k minus 1 to the k minus 1. Well, this guy is, when you plug in 1, you get 1. When you plug in k is 2, you get negative 2, plus 3, negative 4. So you can see it alternates and it also diverges. Okay, so that's why in this case it diverges at the endpoint. So interval of convergence is minus 1 and 1, not including endpoints. So far, so good, everybody? So, let me emphasize. Okay, so the series. This is the series. This is the function it converges to. And this is the interval of convergence. So far, so good, everybody? Always keep in mind that when you figure out the interval convergence, you can use the properties of power series, and you can also use the ratio test. Ratio tests always work. Okay, let's continue. Part E. Integrate the geometric series term by term and identify the function it represents. Okay, let's put one more time here. So k from 0 to infinity, x to the k. That's 1 plus x squared plus dot dot dot. That equals to 1 over 1 minus x for f to the of x less than 1. Okay, so we integrate the series term by term. When we integrate it, well, what's the integral of 1? X, right? Integral of x squared over 2. Okay, integral of x squared, x cubed over 3 plus dot dot dot. Okay, so here we integrate. Okay, so term by term. Okay, so here, the previous example, we differentiate. Okay, so yeah, I want to put it down in case some of you want just read the notes and know what we are doing. Okay, so when we integrate k star from, we also don't know what it starts from. So, but when we integrate x to the k, we add 1 to the exponent and divide it by the new exponents. Okay, so now to figure out the k, what's the index start with? Look at the first term of the power series. Well, compare with this formula. It corresponds to what? K equals 2, because x to the 1 is like k is 0, right? So that's why we know that k start with 0. Okay? So we look at the first term of the power series to figure out what our index start with. So you can realize that when we integrate, k start from 0. Okay, if our original power series, the index start with 0. So when we integrate, k still start with 0. But when we differentiate, you lose the first constant term, so your k start with 1 in that case. Okay. Okay, so how do we integrate that function? Wow. So this is let me put it down. Oh, let me change back to my purple color. Okay, so that is integral 1 over 1 minus x dx. So you can think of your u. This is your u. So that's why you want to have du on top. Then you need minus 1 dx on top. Then you have a negative there. Then you have negative of du over u is ln of absolute value of u. So your u is 1 minus x plus c. So far, so good. We can actually figure out what the c is. So just plug in some x values. So we can plug in some x values. Let's plug in 1. See, because it's ln, you cannot plug in 0. So let's plug in, we cannot plug in 1 because 1 minus 1 is 0. ln of 0 is minus infinity, not defined. Okay, so we plug in 0. We can plug in 0, right? Yes, so we plug in x is 0. Okay, so to figure out c, we plug in this case, x is 0. Then all of the series, because x, they're all powers of x, then those are 0. Okay, 0, 0. And on the right hand side, minus ln of 1 minus 0 plus c. ln of 1 is 0. Oh, it tells us that c is 0. Good. So then that's why we have the function it represents is minus ln of 1 minus x. That equals to the series k from 0 to infinity, x to the power of k plus 1 over k plus 1. So far, so good, everybody? Okay, so we find the series and we find the function. We also need to find the interval of convergence. We know the series converges, okay, for the interior point, so minus 1 to 1. Okay, but how about at the endpoints? We gotta check that. So let's check that at the endpoints. Okay, at 1, well, we plug in the series. We plug in x is 1. Then we have 1 over k plus 1. Oh, when we plug in minus 1, we have minus 1 to the k plus 1. So far, so good. So actually, they are p series. If you realize, if I change my k, if I let my k start with 1, then my expression changed to 1 over k. Oops, sorry, I forgot about this. And I change my k from 1 to infinity. I get minus 1 to the k. And then over k. Okay, so it's exactly a p series. Remember, we look at the term, the series with the positive terms. The p is 1, so by the p test, series diverges. Okay, but then look at this guy. We use the alternating series test because the limit of 1 over k is 0 and the 1 over k is decreasing. So by the alternating series test, this guy converges. Oh, so what is the interval of convergence? We have -1 converges, so bracket there, and 1 diverges, so parentheses there. So you can see when we differentiate or integrate a series term by term, the interval of convergence might change at the endpoints. Okay, we know the interior will stay converges, but the endpoints, we might have maybe at some points it converges, maybe at some points it does not converge. Okay, so we also need to check the endpoints. So far, so good. So now we learned how to use the properties of power series to figure out the functions and the series it represents. Okay. All right. So that is session 9.2. So let me go back to our picture. So this is a picture, right? So this chapter, we want to learn the relationship between functions and power series. So now we talk about one direction given a function. How do we find a power series represent this function? Well, we can use the common power series formula, and we can use properties of the power series just like what we have been doing. And in session 9.3, we will talk about Taylor series formula. Then we will talk about that more. However, the other direction, given the power series and find the function that the power series represents, in this direction is hard. Okay, so we will talk about some example in session 9.4. That's our plan. Bye.